pleasure to present our work, which is about the practical software model checking through dynamic interface reduction, which is a novel technique to improve the efficiency of the model checkers. So this is a joint work between the Microsoft Research Asia and Columbia University. So nowadays, distributed system has already been extensively deployed and formed the foundation of the infrastructure for the large-scale data processing and storage. However, building a reliable distributed system is notoriously very difficult. This is mainly because there are huge numbers of non-determinism existing there. For example, the machine can fail and crash, and the network message can be lost and delayed. And inside the distributed nodes, the asynchronous I/O can lead to the different orders of the message deliveries. And also, the multiple threads can interleave non-deterministically. So this non-determinism can lead to the very tricky bugs. So in order to improve the reliability of the software system, recently implementation-level software model checkers have been proposed and proven to be very effective for finding bugs in the existing distributed system implementation. For example, the MIS-MC and the MODIST are two representatives that has been published recently. The advantages of these kind of tools is that they can directly track the system implementation without requiring the user to construct some abstract model beforehand, which could be a daunting and error-prone process. So for example, the MODIST can directly instrument the target system implementation and have a back-end state space explorer to control the execution of the target system. And at each execution step, it will enumerate the different execution orders of the current non-deterministic events in the system and repeat this process until it has explored all the different executions, all is stopped by the users. So the state space is the number of different executions that we have to explore, and it is exponential to the number of execution steps. So although the implementation level software model checker has found some new bugs for the existing distributed system implementation, we still cannot know whether there are more bugs existing there. So the problem is that the state space is too big and we cannot fully exploit it. We have some painful experience when we model check the system, which is called MPS. So MPS is a product level Paxos implementation in Microsoft, which has been deployed in Microsoft for many years and have managed tens of thousands of machines. And the Paxos is a distributed consensus protocol. And we have model checked the MPS with a small configuration settings with three distributed nodes, and we have bound the system state with some meaningful logical state space bound, and that we believe the system can still allow to exercise most of the logic of the Paxos protocol. However, we have never fully explored the MPS with three nodes and under this logical bound. So we have estimated that this would take us 34 years to finish this exploration when we use MODIST. And so it's clear that we cannot afford to wait that long. So to attack this problem, we have proposed a novel state space reduction technique, which is called a dynamic interface reduction. So here I would like to first list some important and good features of this technique. So firstly, it is very effective. And with this technique, we actually have managed to fully explore the state space of MPS with three nodes only in 18 hours. So compared with the 34 years, it's clearly a huge speed up. So this is attributed to the state space reduction ratio that we have achieved. For example, when we apply this technique for model checking the MPS and the Berkeley DB with its replication manager enabled, we actually achieved the hundreds of thousands of times state space reduction. And also, the dynamic interface reduction can be automatically applied to the system implementation without much user interference. So this is consistent with the philosophy of the implementation level software model checkers. And we also proved in our paper that this technique is sound and complete. So by sound, that means it can, we do not introduce any false positives. So any bug that we have found is actually a real bug. And for complete, we mean that if it can finish the exploration for the with some logical state space bound, it can find all the can fully explore the substate space of the target system with this logical state space bound. And since the dynamic interface reduction is the general state-space reduction technique, it can be very easy to be integrated into some different legacy model checkers. We actually have built a model checking system, which is called Demeter, to integrate this dynamic interface reduction with Modest and MIS-MC to demonstrate these good usabilities. So when building the Demeter, the modification for the existing model checkers can be very small, so this integration can be very easy. Okay, so this is outline for the rest of the talk. And I will first talk about the insights that inspires our ideas, and followed by the challenges that we have to attack. And then I will talk about some details of the dynamic interface reduction, and followed by the, and finally I will report some basic evaluation, and followed by the related work and the conclusion. Okay, so the major insights that we have taken is that distributed systems are normally designed and implemented in a modular way. For example, a distributed system can contain multiple processes running on different machine nodes, and each process can be naturally treated as a component. And these processes or the components can communicate with each other through some well-defined interface, such as the message passing. So the message traces between these process or components actually represents the interface behaviors between them. And inside each component, there could be a lot of local non-determinism caused by the multi-threading and asynchronous I/O. So we have noticed that a lot of local state change that caused by this local non-determinism actually do not propagate through the interface. So for example, empirically, when we model check in Berkeley DB, we have found that in average, only 1 out of 1,000 local state change could propagate through the interface. So this means that a lot of local states and the combination of them actually can correspond to the same interface behavior. In other words, the interface behaviors between the components can be much simpler than the local non-determinisms inside each component. So this brings us huge opportunities to reduce the state space that we have to explore if we can construct the interface behaviors for the components and check them separately. For example, if we suppose that we have only one message trace between the 3 components as shown in this figure, and the local state space of the components are the M1, M2, and M3 respectively. If we have to check the components together, we have to explore the total the state space as the M1 times M2 and times M3. So this is because for any local state change, we have to re-explore the rest of the system because we don't know whether this local state change will influence the other components. However, if we can check these components separately, we only have to explore the state space as the sum of them. So there's huge reduction opportunities here. However, there are still some challenges that we have to attack to achieve this component-based reduction. The first challenge is that how can we discover and construct the interface behaviors of the component? So one might think that we can use some manually or statically methods to construct some interface process to simulate the interface behaviors between the component and the rest of the system. However, the manual method could be tedious and error-prone, and the static method actually does not scale and in practice cannot be applied for the large-scale distributed system implementation, which often have tens of thousands of lines of code. Another challenge is that since we have to explore each component separately, how can we guarantee the completeness and the soundness? So to attack these challenges, our solution actually takes a dynamic mechanism. So generally speaking, during the exploration of each component, we actually run the real code of the target system, and we discover the different interface behaviors between the component and the rest of the system, and we combine all the interface behaviors of the components together if possible, and at the same time, we guarantee the correct dependency information for them. Okay, so now let's look at some details about this dynamic interface reduction. I will first give you a high-level overview about this process and then use a concrete example to illustrate it in more detail. So basically, the dynamic interface reduction contains 2 modules. So one is the global explorer, the other is several local explorers, and each global explorer is for each component. And the global explorer is in charge of exploring all the possible global interface behaviors between the components. And for each discovered interface behavior, the global explorer will project it into some local interface behaviors for each component by removing the part of the interface behavior that is irrelevant to the target component. And then the global explorer will dispatch these projected interface behavior to the corresponding local explorers. And the local explorer will explore the local state space for the target component. And in our implementation, we actually reuse the state space explorer of the existing model checkers like Modest and the MIS-MC. So our local explorer actually can run the real code of the system. Therefore, it is very easy for it to generate sound and complete local execution under this given interface behaviors. And during the local exploration, the target component may send new message to the other components. So in this case, it discovers new interface behaviors from the target component to the rest of the system. And then this new interface behavior will be sent back to the global explorer. So in order to discover all the possible global interface behaviors between the component, the global explorer have to combine this new interface behavior with all the existing global interface behaviors to generate the new ones, and at the same time guarantee the dependency information between the events in the interface behavior. And the process will iteratively going on until the whole system reaches some fixed point. And during this process, the global explorer can dynamically discover a complete set of the global interface behaviors, which are also sound. And also because our local explorer actually leverage the existing implementation level software model checker, so the whole process actually does not require any user interference. Okay, now let's look at some concrete examples. So this is a piece of code which implements a simple target system, which contains three components: the client, the primary, and the secondary. The client will send the different sequences of numbers to the primary, depending on the return value of the truth function. So if the truth function returns 0, it will send, the client will send the sequence of 1, 2 to the primary. Otherwise, it will send the sequence number of 1, 3 to the primary. And the primary contains two threads. The main thread will receive the number sent from the client and add this number to the variable total, and then forward this number to the secondary. And the checkpoint thread will concurrently log the current value of the variable total to some persistent storage. And the secondary actually shares the same code with primary, so it behaves similarly, except that it will not forward the received numbers to the other components. And because the main thread and the checkpoint thread will concurrently access the shared variable total, so they need some critical section to protect this access. So for simplicity, we mark this critical section in main thread as the sum, and the critical section in the checkpoint thread as checkpoint, as shown in these gray areas. And in order to bootstrap this process of the exploration, the global explorer has to produce some initial global execution trace to generate the initial global interface behaviors. And it achieves this by just randomly execute the target system. So for example, the initial trace could like this. So the truth function of the client will return number 0, and the client sends the number 1 to the primary, and the primary receives number 1 from the client, and the checkpoint thread of the primary log the current value of the variable total, and it then add the number 1 to the variable total and forward this number 1 to the secondary. The secondary receives this number 1 from the primary, and the checkpoint and sum it. And the similar execution is for the following number 2. And inside the initial global trace, if we only look at the events that involves message passing, as shown in this figure as the bold statement, they actually represent the they actually form the global message trace between the components, which represents the global interface behavior between them. So the global explorer will then project this global message trace into several local message traces for each component. So the local message trace for a component only includes the message event that between the target component and the rest of the system. For example, the local message trace for the primary only includes the message event that the primary received number 1 from the client and forwarded this number 1 to the secondary. It then received number 2 from client and forwarded this number 2 to the secondary. So this is similar for the secondary and the client. And then the global explorer will dispatch these projected local message traces to the corresponding local explorer for local exploration. So the local explorer then will explore the local non-determinisms for the target component and follow the execution of the given local message trace. So let's first look at the local explorer for the primary. it enumerates the different execution orders of the checkpoint operation and the sum operation because they belong to the two different concurrent threads. As shown in these slides, there's totally 3 different permutations of these local operations. And the different executions of these local operations actually do not generate new interface behaviors from the primary to the rest of the system. So the local explorer for the primary actually can follow the execution of the given local message trace without any problem. And this is similar for the secondary. But there's some difference for the local explorer for the client. So the client has 2 local states. It depends on the return value of the truth function. So if the truth function returns 1, it leads to that the client will send the number 3 to the primary, so which is a network event that does not exist in the given local message trace. So actually, this execution generates a new message trace that we call a branching message trace. And the new message event, as shown in the red color, is called the branching message event. And then this branching message trace will be sent back to the global explorer. And in order to discover all the possible global message traces, the global explorer have to compose this branching message trace with all the existing global message traces. So in this concrete example, it's just compose this branching message trace with the initial global message trace. So the process of this composition actually trying to find a common prefix between the branch message trace and the existing global message trace, and replace the message event at the deviating point with the branch message event. And in this new message trace, the last 3 message events in the existing global message trace has to be removed because they depend on the message event at the deviating point, which has already been replaced by the branching message event. So this is the generated new global message trace. So through this way, the composition can generate a message trace that is also valid because we actually track the dependency information between the message events. And then this new message trace will be projected to the local explorers and for local exploration again. So this is the whole process of the dynamic interface reduction. And now let's look at some evaluation results. So for Demeter integrated with Modest, I will report the result for model checking the MPS and the Berkeley DB. And for the Demeter integrated with MIS-MC, I will report the result for model checking the code implementation on the MACE. So here is the result for the effectiveness of the dynamic interface reduction. The table shows the reduction ratio when we apply this reduction technique for the different applications. So app-n represents the application running with n numbers different components. And the reduction ratio actually is the state space without dynamic interface reduction divided by the state space with a DIR. So as shown in this table, the reduction ratio for the applications with 3 components can be much more significant than the reduction ratio for the applications with 2 components. This is mainly because our reduction technique reduced the total state space by from the product to the sum of the local state space of the components. So it increases within the increasing number of components. And we can also see that the reduction ratio for the MPS and the Berkeley DB can be much more significant than the reduction ratio of the code. So this is because the product level distributed system implementation like MPS and the Berkeley DB often introduce a lot of local non-determinism inside each component by applying the multi-threading and the complex asynchronous I/O. And the second row shows the runtime speed up that we can achieve for this reduction. And we can see that the number of the speed up is relatively smaller than the number of the reduction ratio. This is because our dynamic interface reduction can introduce some constant overhead, which can make the running time of each explored execution a little bit longer. However, our technique can still win because we allow the model checkers only have to explore much fewer executions. Okay, then I will talk about some related work. So the idea of model checking each component separately is borrowed from the compositional model checking, which is from the traditional model checking community. However, their method actually require the user to construct some interface process beforehand to simulate the interface behaviors between the component and the rest of the system. So their technique actually does not scale for large-scale distributed system. Another line of related work is a orthogonal state-space reduction technique. One of the famous one is the partial order reduction. But partial order reduction is still global exploration policy. So if some local state change happened inside the component and do not propagate, it will have to re-explore the rest of the system. And another more recent related work is from the NSDI-11. Researchers actually, some researchers have model-checked the network system on maze by separating the exploration of the system state and the network state. They constructed the network state by just making up the network events and without tracking the dependency informations between them. So their method is not sound. So they need some post-process to revalidate the bugs that they have found, which could be a false positive. Okay, to conclude, we have taken the observation that the distributed systems are normally designed in a modular way, and a lot of local non-determinate systems actually do not propagate through the interface. And with this observation, we proposed a dynamic interface reduction technique, which is very effective, and it helps us to fully explore state space of a product level Paxos implementation in 18 hours, which could be a 34 years work if without this technique. And it can also be automatically applied to the targeted system implementation. And then it can also be easily integrated into the existing model checkers. And we have also proved that this technique is sound and complete. We then built a model checking system called Demeter to integrate this dynamic interface reduction to the MODIST and the Maze MC to demonstrate this good usability. Okay, so that's all. Thank you very much.
George Candea, EPFL. So your colleagues at MSR Redmond described a few years ago in POPL something called compositional dynamic testing, where they basically look at functions as essentially independent modules and then try to characterize them, basically analyze them in isolation, and then generate these function summaries that are basically pre-post conditions, and then use this to cut the search space. Now, of course, that's in the domain of symbolic execution. This is model checking, two different things. But I'm wondering, at the level of the idea, whether you think these two approaches are similar and, in effect, cut down the search space in really the same way.
Actually, I think I know that work, and I think this the idea is actually similar, but it's just in a different area. And I think the major difference is that work actually cannot discover the concurrency bugs. So the symbolic execution cannot cover the concurrency state, right?
Well, actually, I mean, I think that's completely orthogonal. I mean, you can use function summaries when you do the exploration of the concurrent search space as well. They just didn't need to at the time. But in essence, and I think this is what's very cool about this work and also the other, is that you are cutting down your space, your exponential explosion into modules, and that leads to the isolation of the explosion, right? And that's why we have modularity. I was just wondering if it's really a very similar idea in a different domain or not, and you seem to think it is somewhat related.
It is similar. Yeah.
Okay, thank you.
Yeah.
Any more questions? Okay. Thanks, Ming. Great talk.
I have a question.
Right.
Meysam Yabande from Yahoo Research. Can you explain more how your algorithm works on top of Maze? Because as far as I understood, the main focus of the algorithm is to optimize the cases that you have multiple threads on a single node. And in Maze application that are event-based, you have a single thread. So how does it work on top of Maze?
But although you mean the Maze state machine is a single thread, right?
Yeah, there is an event-based implementation.
Yeah, but it is event-based. So for the different the distributed nodes for each node, it is actually, but still has a lot of local non-determinisms, right?
But there is a single thread.
Yeah, even it's a single thread, but the maze also will, for each node, will explore the different orders of the concurrent event, right? So, for example, the different node may send message to a single node, and it can enumerate the different orders of this message, right?
Yes, that's true. But I couldn't understand how this algorithm applies to that case. I understand how it works when you have multiple threads, but when you have single thread, I couldn't understand it. Perhaps we can continue offline.
Hi, I'm Huayang. I'm for other paper. I think I answered your question. So in native code, in Modest, we focus on native code which is driven by multi-threading or multiple process programs. But actually, Maze is an event-driven system. So Maze models the system has different nodes, and each node has an event queue. The events in the queue can be each of the event in the queue is equivalent and can be executed in the same time. That builds the concurrent model of Maze node, right?
Yes. Yes.
So we just model Maze node as a general transition system in which each time we take an event from the queue and we treat it as a transition of the system.
Yes, yes.
So that's my answer.
Yep. But what is the key idea of the algorithm that applies to that case as well? No, if you have a multi-threaded system, I understand how the key idea of the algorithm applies to that. But maybe we can take it offline, it's better.
Yeah, sure.
Yes.
Okay, thank you.